linear, and therefore you have nonlinearity in the problem due to the material, which is classified as material nonlinearity. Geometric nonlinearity arises because your deformations are large. So deformations are large. And it is this part of the problem that we will have to consider in this chapter on continuum mechanics, which I am going to spend quite a bit of time on. This will tell you how large deformations are handled in the framework of solid mechanics. Okay, so some conventions that I'm going to follow. First is these people just keep on entering. So from next time onwards, I'll just not allow. Do you know if there's a way of letting these people enter the class without bothering me?
Sir, you can turn off the waiting room, then anyone can enter, but you won't have any control.
I can turn off what?
The waiting room. In the settings, you can security options, you can turn off the waiting room.
Okay, let me try that. This is really irritating. In settings, you are saying, right?
Yes, sir.
Where are the settings?
There will be something called the security options or something like that.
Security option, okay. In a disabled waiting room, okay, good. So let me talk about a few conventions that we are going to follow. We are going to look at a rectangular right-handed Cartesian coordinate system all the time, and we will denote the base vectors by E alpha, where alpha goes from 1 to 3, and this is a fixed reference frame. So whenever we denote the base vectors by E alpha, we are referring to a fixed reference frame, which is right-handed orthogonal Cartesian, and is not changing with time. It's not changing with time. So E alphas are fixed vectors. We will talk about different configurations of the body. We will talk about the reference configuration or the undeformed configuration, and the undeformed configuration we will denote always by this symbol B naught, and we will also talk about the deformed configuration, which we will also call the current configuration, and we will denote that by B. We will have to deal with the volumes of these bodies, so B naught and B, the reference and the current configurations, and the volumes would be denoted by subscript 0, omega 0 and omega respectively, and the surfaces will be denoted by del omega 0 and del omega. We will denote all quantities associated with the reference configuration. Okay, that I'll explain a little later, but as of now, all tensors will be denoted by bold capitals, and vectors will be denoted by small Roman letters. What we are going to look at is continuum mechanics, and we will take a quick tour through continuum mechanics. Not very quick, but quicker than in a normal course on continuum mechanics. So continuum mechanics is a technique which um, is used for understanding the material deformations and the forces that are needed to cause those deformations by smearing out the atomistic details. So matter is not discrete in continuum mechanics. Matter is a continuum. So there is no discreteness of matter. So we are at a length scale where we cannot see the atomistic details explicitly. So that's one um, one assumption that we will always make. Okay, so if when we don't see the atoms, we have a bunch of points that are connected to each other, which make up a body, and at every point we have the existence of displacement or velocity fields which are continuous, which means that the change by small quantities if you move by small distances. So you have vectorial displacements or velocity fields, and the forces exerted on one part of the material is transmitted to other parts through the existence of tensorial stress fields. And again, these are continuous quantities. They are continuous functions of position and possibly functions of time as well. But the discreteness of matter is completely thrown out of the window. So with that assumption, with that understanding, we will now draw this picture of a body which is in this configuration at time t equal to 0. It is called the reference or initial configuration. And at some time, some later time, it deforms into this configuration, which will be called the current configuration. Now, there are various ways of describing this problem, but the way I will adopt is that both these configurations are described in the same coordinate system, denoted by base vectors E1, E2, E3, and a point P, capital P, in the reference configuration is mapped into the current configuration due to the deformation or the motion to a point small p. The reference configuration is the volume of the reference configuration is omega naught, and the volume of the current configuration is omega. The position vector of this point, capital P, with respect to this fixed coordinate system is denoted by capital X, and the position of this point small p is denoted by small x. So this is a convention that we will try to adopt, where capital letters will denote quantities associated with the reference configuration, and small letters will denote things associated with the current configuration. Unless it causes some other confusion, we will try to stick to it. Now, the reference configuration is mapped to the current configuration through a mapping function called chi, and this chi is called the motion. What kind of a quantity is chi? Chi takes a point in the reference configuration as its input and tells me what is the position of this point in the current configuration at some time t. In other words, chi tells me what is small x. Chi takes in capital X and the time as its inputs and tells me what is small x at that time. So it basically tells me where does the motion take capital X to. So if capital X is taken to small x, it just tells me where it takes it to. So this function is called a motion, and this is obviously a vector function because x has 3 components. So we can write it in tensor notation, initial notation, as chi I, which is a function of capital X and T. So we can either write it like this, or we can write it like this, where chi I is a function of capital X1, capital X2, capital X3, and T. Now, we assume that this motion is one-to-one and therefore invertible, which means that we assume that every point P goes to one and only one point small p. Okay, so this can be violated in certain situations. For example, during the motion, the body breaks into two parts. So the body breaks along a curve like this. So this point P, half of it, some of it will lie in the upper part and the rest in the lower part. So it's possible that P splits into 2 points. Similarly, it is possible that I have a P which is here, and during deformation, this part of the body comes in contact with this part of the body, which means that this P, which was 1 point in the reference configuration, this P and this P prime, let's say, which were 2 points in the reference configuration, in the current configuration come into contact and become 1 point. So these are situations in which the one-to-oneness of this motion will be disrupted. We are not considering those kinds of situations, and we are strictly considering that for every capital P, there is only one and only one small p. So that will also imply that for every small p, there is one and only one capital P, which means that this motion as a mathematical mapping is also invertible. So this is the motion, and this is the inverse of the motion. Chi inverse is the inverse of the motion. So it takes small x and t as inputs and spits out capital X as an output. So this motion exists, and it is also invertible, which means it is one-to-one. Okay, this is the understanding with which we will proceed. Now, let's take an example of a motion. This is a block of material. It's a two-dimensional, it's a long block, so it extends infinitely in the x3 direction. So this is your initial block. Okay, and you have deformed it to the dotted line. So you have sheared it at the top, and it has taken the shape of this rectangular parallelogram. Not rectangular parallelogram, just parallelogram. Okay, so my omega naught is the rectangle, this one, and omega is the dotted parallelogram, and this angle is given as theta, which can be changing with time. So as time passes, this parallelogram tilts more and more to the right. Okay, now this can be expressed as a motion. So remember, motion is some function chi of capital X t. So I have to take a point in the reference configuration, which is the red one, and t, and have to be able to say what small x is going to be. If you look at this motion carefully, let's take a point here. Since it's shearing to the right, this point in the deformed configuration would probably end up here, so that its vertical height in the x2 direction remains fixed. Of course, its position in the x3 direction, which is perpendicular to the plane of this figure, also remains fixed. So small x2 remains equal to capital X2, small x3 remains equal to capital X3, and every point moves in the horizontal direction by this amount, which is given by x2, capital X2 tan theta, where capital X2 is the height of the point in the reference configuration. This capital X2 remains the same, but then the position of the point changes by this angle theta. So capital X2 tan theta gives you this distance. So small x1 will be given by capital x1 plus capital X2 tan theta, where x1 is this distance. This is x1. So this is your motion. And if you want to write it in a vectorial manner, if you want to write the chi, so chi would be a function of capital X. So that can be written as this is small x1 E1, x2 E2, x3 E3. So this will be your function chi written in the vectorial form. This is known as simple shear. This motion is known as simple shear, something that you may or may not want to remember, but this is known as simple shear. Okay. Now let us do it the other way. Let us write down a motion. This is a motion that I've written down, and let us try to imagine what this motion is going to do. Okay. Now, motion acts at all points on the body. The motion does not depend on the shape of the initial configuration. Okay, but if I want to draw the motion, if I want to depict the motion on the screen, I have to assume some shape of the initial configuration. That shape is not important. I'm going to assume a rectangular prism. And I am going to show what this motion does to the prism. Okay, and in order to show that, since I'm using a rectangular prism, you will see some kind of a deformation, but it has got nothing to do with the rectangular prism. I could have started with a sphere and tried to show you the effect on the sphere or some other shape, any other shape. I thought that rectangular prism is the nicest way of depicting this motion pictorially. That's why I'm using a rectangular prism. It's not that the motion is tied in any way to the shape of the body. Okay, so what do we have here? We have the deformed coordinates dependent on cos alpha x3, sin alpha x3. So x3 is the height of a point along the rectangular prism. So if I draw it, this is my rectangular prism. This is my x3 and x1 and x2. Okay, so x3 gives the height of rectangular prism, and at any time a point remains at the height it was in the undeformed configuration. So that is given by the fact that small x3 is always equal to capital X3. Now, if you look at this, small x1 and small x2 are obtained by rotation of x1, capital X1, capital X2 by an angle alpha x3. So what we have here is a motion where every point, any point on this or at a height x3, every point at a height x3 remains there, but rotates by an angle alpha x3. Alpha x3 is an angle that depends linearly on the x3 coordinate. Therefore, cross sections at the top rotate more than cross sections below it, and the cross section on the xy plane does not rotate at all because x3 is equal to 0 there. So this is a deformation which will take it to something like this. Cross sections at the bottom will not rotate at all. And as you grow up, as you go up, the rotation is going to increase, and every cross section will remain flat and rotate by an angle that is proportional to its initial height. So I did this example so that you get some practice in visualizing a motion when you see a mapping equation of this sort. That's quite important. Now, we can look at motion from 2 points of view, and these points of view are called Lagrangian and Eulerian. Okay, so position in the Lagrangian description, which is also called a material description, will be denoted by capital X, and in the spatial or Eulerian description, it will be denoted by small x. So the thing that I am trying to do is, I am trying to ask, and going back to this story, in one case, I am concentrating on the current configuration, and I am taking a point small x, and I'm asking questions about this point. For example, I'm asking what is the stress in this small box around this point, or what is the displacement of this point, what is the velocity of this point. So I am asking about things connected to small x. That's the spatial description, where I am trying to express all quantities as functions of small x. There is another possibility where I take this point and I ask what is its velocity going to be at a time t when its initial position is known. So I know capital X. I want to know what will happen sometime later to its velocity. So that means I am trying to write velocity as a function of capital X and time rather than small x and time, and that's known as the material description. So I have now, since I have two configurations, I have two ways of writing every quantity. One in terms of the initial coordinates of a point, one in terms of the final coordinates of a point. For example, if I want to write the displacement, let's say, so I can write the displacement as in the Lagrangian description. So I'll denote it by capital U. In Lagrangian description, things are functions of capital X, the initial position of a point, and time. So given, if I know the initial position of a point, I will be able to get this Lagrangian displacement, which is the difference between the final position of the point and its initial position, where the final position is a function of capital X and t. So this is a Lagrangian description of displacement field and is a field over capital X. Capital U is a field over capital X. Now I can change it back and say that, okay, capital U can be also written as the same function with this capital X replaced by chi inverse of small xt. Remember, capital X is chi inverse of small xt. So I can use this chi inverse function and express this capital U now in terms of small x. So implicitly it becomes a function of small x, and therefore I can write it as another function, a different function, small u of small x. So this would be the spatial displacement. Okay. So the same quantity, the displacements are the same. The displacement of a point is the same. Here I am inputting the initial position of the point to get its displacement at some time t. Here, I am putting the final position of the point, current position of the point, and the time t to get the displacement. I should get the same displacement in both the cases, but my inputs are different in the two cases. That's the difference between the Eulerian and Lagrangian descriptions. Now I can do this for other quantities also. So I can write v, for example, velocity of a point which is initially located at capital X. So to do that, I have to take, I know that small x is equal to a function of capital X and t. So I'll use this function, take its derivative with respect to time, I get the get the velocity. I take the velocity, take this velocity, which is a function of the initial position, take its derivative again, I get the acceleration. Okay, so these are all functions of capital X, and therefore they are material velocity and material acceleration. Now to convert this into spatial quantities, I will now have to use the motion that I know. So I'll have to replace these things by chi-inverse small xt. I'll have to replace them by chi-inverse small xt, which is what I have done here. Once I do that, I get a different function, which we'll call small b, which are functions of small x and t. So these are your spatial velocities and spatial accelerations. So value-wise, I mean, as vectors, both capital V and small v are the same, but the inputs to it are different. That's what you have to keep in mind. Now let us do a problem to understand this a little bit more. Okay. Okay. Anyway, before I do the problem, I should ask: do you have anything to ask me about what we have done so far?
Hello, sir. Excuse me.
Yeah, Akshay.
Sir, on this page itself, when we are defining the capital U vector, so the function is denoted using the Greek letter, and we have used a small x to denote that function.
Sorry, I don't get it.
So, like in the second formula, we've used the Greek letter for.
Okay. So this is what confuses you.
Yes, sir. Yes. So.
Okay. So it's the same thing. It's the same thing. It's just a way of writing. So I am writing this directly. So this x will be a function of capital X and t, right? So most of the time I'll not write this chi. I'll just write x as a function of capital X and t, which means the same thing. This is the motion. This is the motion. Okay. It means the same thing. So I could have written chi here. Chi capital XT would have meant the same because X is equal to chi capital XT. Right. So I'll do this pretty often. When there's no chance of confusion, I will write X directly rather than going through this chi. Okay.
Okay, sir.
Okay. So here is the problem that we want to do. So here is a motion. Okay. This is a motion. And we will find the velocity and accelerations in the material and spatial descriptions. So material description, what do? We use this idea. that the velocity in the material net is the motion derivative of the motion with respect to time. So to get capital V1, I will do del x1 del t. So del x1 is already a function of capital X and time. So I take just derivative of this with respect to time, and I will get et capital X1, and there's a minus here, so plus e to the power minus t capital X2. That's what I got. So this is del x1 del t. So I'll do del x2 del t, which will be et x1 minus e minus t x2. So this is del x2 del t, and it's a function of capital X. And x3 is not a function of time, so v3 would be equal to 0. So this is del x3 del t, and these are functions of time. Okay, functions of capital X and time. Okay, accelerations, one more derivative, of course. So these are already functions of capital X1, X2, X3. So take one more time derivative, and this is what you will get, I think. So this is your del capital V1 del t, del capital V2 del t, and this is 0, of course, del capital V3 del t. Right now, let's look at this. V1 is equal to e to the power t capital X1 plus e to the power minus t capital X2. Now, if I want to now convert this into spatial description, I'll have to use the equations for capital X1 and capital X2, okay, in terms of small x1 and small x2. So what I see, because I have chosen this deliberately to make my life simpler, I see that this is exactly equal to small x2. So I don't have to do the elimination of capital X1, capital X2 from here. I know it directly that small v1 can be written as just small x2, because this function is exactly this. Similarly, small v2, this is small v2, and you can see it is exactly equal to small x1. So v2 is equal to small x1, and v3, of course, is equal to 0. So this is my spatial description now in terms of the small x's. And you can convert from one to the other if you know the motion. Okay. Similarly, if you do accelerations, this quantity is equal to x1, as you can see. This quantity is equal to x2, and small a1 is x1, and small a2 is x2. Small a3 is, of course, equal to 0. Okay. So so this is conversion from Lagrangian to Eulerian, or material to spatial coordinates. Okay. Now,
so can
this,
you go back to the previous slide, the one before this? Yes. Just give me a second.
Hello?
Yes, sir. Yes, sir. Just one second. I'm catching into something.
I'll put this up. I mean, I'm recording it, so this will be available to you later. So and the slides as well.
Focus.
You don't have to write things down. Okay. So now what I'm going to do is I am going to show you the animation that I've made in MATLAB of this motion. And you will see the animation as time passes. So I am increasing this t, and as I increase this t, I am plotting the the x1, x2, x3 of the body. The body that I consider is a rectangle, is a square actually, a 1 by 1 square. And I want to show you how this 1 by 1 square deforms. And what I have done in the MATLAB program is that I have taken the corners of the rectangle, corners of the initial rectangle, found their velocities as time passes, and I'm going to show you how the deformation looks like. So this is how it goes. The initial red that you just saw for flashing for a while is the initial configuration, and the yellows are the deformed configurations. And these arrows that you see, there are arrows here as well. These are the velocities of the corners of, obviously you see this corner has no velocity. This corner is fixed. That will be clear from here. If you put x1 and x2 both equal to 0, v1 will be 0, v2 will also be 0, v3 is anyway 0 for all x's. So the corner at 0, 0 does not move at all, has no velocity, no acceleration. And the other corners have velocities which are indicated by these arrows. So these are the instantaneous velocities at these times of these corners. And this is how the deformation is happening. So this is the motion that we have described through these set of equations. Okay. So and we can describe any kind of motion through equations of this sort. Okay. Now what I am plotting here are the Lagrangian velocities. So I have calculated the velocities using these equations. Using these equations, I've calculated the velocity in my MATLAB program and are plotting them. Right. Now, let's look at another example to understand this a little bit more. So this is a motion. Again, x3 is equal to capital X3. So I'm not writing it. So this is a two-dimensional situation. Okay, k is a constant, and then again let's find the Lagrangian velocities of a point. So I take derivatives of this with respect to time. This is not a function of time, and this will give you 2 x2 squared into k into t. So that's what I have got, and I do derivative of this with respect to time. I get k capital X2. So these are my material velocities, the components of my material velocity. V3 is 0 because this is not a function of time. Okay. Now I want to convert this into spatial quantities. What I will do is, now I will have to solve for x2 from these two equations. I'll have to solve for x2 in terms of small x1 and small x2. And if I do the solution and plug it in here, plug the value of x2 in terms of small x1 and small x2 here, these are the Eulerian velocities that we will get. So you can try doing that yourself. And these are the Eulerian velocities that you get. Okay. Now, what exactly is the difference between these two velocities? There is actually vector-wise, as I said before, vector-wise, the two velocities are the same. It's a velocity of a point. So it's a velocity of this point. In one case, I am asking that this point was initially at 1, 1, 0. So I am asking the point that was initially at 1, 1, 0, what is its velocity at 0.5 seconds? That is my material question. In the other case, I am asking what about the point that is here at 0.23 seconds? What is its velocity? In both the cases, the answer should be the same. The point that was at 110 at 0.23 seconds will have the same velocity as the point that is, let's bring it back to 0.23 seconds. Okay. Now, this point now has the same velocity as the 0.110 at 0.23 seconds, but the functions that describe the velocity are different. Okay, so this is what I have done here is I have plotted the blue arrows. I hope this will play. Let me see if this plays. Oh, okay, this doesn't play. Okay, Zoom, it's playing on my computer, but it doesn't play when I share it. Okay, maybe I try to show you in the, maybe you will have it in the, in your notes. The description is given here, you can go through it. Can you guys see my screen?
No, sir.
No, sir.
Oops. Now?
Yes, sir.
Yes, sir.
Yeah, so this doesn't play, I'm sorry. But the description is given, so you can watch it when I upload these notes. Okay. Right. So for our purposes, these two different descriptions, the Lagrangian and Eulerian descriptions, are important. When we frame finite element problems in nonlinear mechanics, we need to make distinctions between Eulerian and Lagrangian descriptions. And what we will learn in this course are mostly Lagrangian methods of solving problems in finite elements. However, when people do similar problems in fluid mechanics, they prefer to use the Eulerian description. Now, when you have a Lagrangian description, when you want to frame something in the Lagrangian description, you can think of it this way. This is the body that you are, let's say this is the initial configuration of the body, and these black lines are your finite element mesh. Now imagine that this finite element mesh is imprinted on the surface of the body, on the body itself. So that when you deform the body into this shape, the finite element mesh deforms with the body. Every point is attached to, every node is attached to the body, and it's deforming with the body. So the biggest advantage of this is that boundary nodes, a node that lies on the boundary like this or this, remains on the boundary. Okay, it remains on the boundary. Whatever boundary conditions you have, you can apply them at the nodes, because the nodes remain on the boundary. Nodes on the boundary in the initial configuration remain on the boundary in the deformed configuration. The disadvantage is that each element, which is a nice rectangle here, each element is deforming with the body, So this element becomes this, and as the deformation becomes larger and larger, the distortion of the elements is severe, can be severe. And as you probably might know from your basic finite element courses, very distorted isoparametric elements may have problems with its Jacobian. The mapping may not be proper, and therefore that might prevent you from taking the simulation forward. So that is what mesh distortion due to large deformations is one of the biggest problems in Lagrangian descriptions of finite element methods. But the advantage is that the boundaries remain boundaries all through your analysis. Compare that with Eulerian view. In Eulerian view, this is again the body that you are deforming, but it is as if you are looking at the body through a glass sheet on which your finite element mesh is created. Okay, so your finite element mesh is created on a glass sheet, and you're looking at the deformation of the body through this glass sheet. So the body deforms in this manner, but your mesh does not get distorted at all. Only the amount of material in every element keeps on changing as time passes. So it is a way of preventing the problem with mesh distortion due to large deformations. But at the same time, your boundary nodes do not remain fixed as time passes. So because you are looking at a spatial picture, you are looking at the deformed configuration, your boundary nodes are not going to stay at the boundary, and therefore there will be complications in applying boundary conditions. So these are the advantages and disadvantages of these two methods. In solid mechanics, we overwhelmingly prefer the Lagrangian method, and all that we will learn in this course are based on the Lagrangian description, where nodes will be firmly imprinted on the volume of the body. Okay. So we have to do a little bit more on this capital X and small x business. So we will now be able to take different kinds of derivatives. Now, so we will be dealing with a lot of spatial fields. So spatial fields are smooth, continuous, vector, tensor, or scalar functions, which are functions of small x and t. We will also deal with a lot of material fields, which are functions of capital X and t. So we saw examples like small u xt is a continuously varying field, which is a function of small x, and capital U, capital XT is a material field. So these are fields because these are continuous functions varying from point to point dependent on the position. Now we can take several kinds of derivatives. Okay. For example, we can take spatial derivative, spatial time derivative, and spatial gradient of a scalar spatial field. So scalar spatial field is one which takes in the initial, takes in the current position of a point and gives out a scalar. So if you want to take f dot, you simply take del f del t. If you want to take gradient of f, you do del f del small x. Okay. You can take similarly, if you have a scalar function, capital F, which takes in the initial position of a point and the time, you can take its f dot in the same way, del f del t. But when you take the gradient, you take del f del capital X, and just to distinguish between this gradient operator and the gradient operator with respect to capital X, we put a 0 here. So this is the gradient operator which will mean del capital X, and this gradient operator will mean del small x. So we can take these different kinds of derivatives, right? So from the context, most of the time it will be clear whether we are taking a spatial derivative or a material derivative, but we'll need both of them. Okay, we will see how we convert one derivative into another in a later lecture. So also spatial fields, when you want to take time derivatives of a spatial field, you might have learned about the total derivative. The total derivative is necessary because when you take time derivative of, let's say, the velocity field, this quantity is also a function of time. So small x is also a function of time. So when you do the total derivative, when you take this quantity called the total derivative, you use the chain rule. So you say del v del t into dt is 1. Then you do del v del xk del t. So this is a repeated index. Del xk del t is again v. So del v del t is okay. I made a mistake. So let's write it as del vi. Okay. So you can do this for the velocity, or you can do it for any other quantity. So the total derivative is also called the material derivative of v, is contains a spatial part and this part which some people call a convective term, but this just follows from the chain rule. So you have to remember that when you take total derivative of a spatial quantity, you have to take derivative of x as well as derivative with respect to t. So you have to remember that small x is changing with time. Small x of a particle on the body is changing with time. The current position of a particle is changing with time, whereas capital X is not a function of time. Capital X is the initial coordinate. It's not a function of time. So this question of total derivative arises because small x is a function of time. Okay. Right, question so far? Okay, let's see how this affects us. So here's a small problem. A body is spinning with an angular velocity omega t. So consider that you have a rectangle which is spinning about its center at an angular velocity omega. So this are my axis, capital X1, capital X2. So if I take any point, if I take any point capital X1, capital X2, its position in the deformed configuration is given by small xt, where small xt is related to capital Xt by this expression. It's just a rigid body motion by an angle omega t. I'm sure you can visualize this. Okay, now you want to find the velocity. You want to find the velocity by taking the time derivative. So you can do del x del t, which will give you omega times minus sine omega t, derivative of this, then minus cos omega t, then cos omega t, and this is sine omega t. Oh, I'm taking derivative of this. This is cos omega t. That's right. And minus sine omega t. Okay. Times capital X1, capital X2. Okay. So this is what I get. Okay. Similarly, if you want to do the acceleration, you do the derivative of this again, and this is what you get. Okay. And these are velocities and accelerations with which are functions of capital X1 and capital X2. And these have to be equal to the spatial quantities. These have to be equal to the spatial quantities when we convert them, convert the capital X1, capital X2 into the spatial quantities. This is what we have. We have V1 xt and V2 xt. These are components of the spatial velocity. And to convert it, we replace this capital X1, X2 by inverse of this into small x1, x2. So I replace it by cos omega t minus sine omega t, sine omega t, cos omega t, inverse times x1, small x2. That will be equal to capital X1, capital X2. Right? And when you do that, you have to remember that this is a proper orthogonal tensor. This is just a rotation. Therefore, its inverse is its transpose. So you just transpose this matrix and you get its inverse. That's what I have done. So I will take this quantity and multiply it with transpose of this times small x1, small x2. So that is what I have done here. I've taken that velocity, multiplied it with the transpose of small x1, transpose of that matrix times small x1, small x2. And if you do the multiplication, this is what you will get. So this will give you minus sine omega t times cos omega t, and then plus cos omega t sine omega t. So this will give you 0. Here you will get minus 1, 1, 0, and times small x1, small x2. So you will get omega times minus x2 and omega times plus x1. That is the spatial description of your velocity, whereas this is the material description of your velocity. So to get the acceleration, now I will have to apply the concept of the total derivative. So acceleration is the total derivative of the spatial velocity v. So I have the spatial velocity here. From here, I want to get the acceleration. So I have to take its total derivative, which is given by this formula as we have seen before. So now I am going to take these expressions. So I have V1 is equal to minus omega x2, V2 equal to omega x1. So this is what I have, and I will plug it in here. I will plug it in here and try to get the acceleration. So to do that, I'll have to calculate this gradient of V. Remember, this is the spatial gradient because I'm dealing with V as functions of small x. So I'll have to use the spatial gradient here. So to take the spatial gradient, this is what we do. The gradient operator is this. Please remember your tensor. And this is your V. The first component is minus omega x2, and the second component is omega x1. And then if you do this derivative, this is the gradient that you will get. Gradient is a second order tensor, remember. So E1, E2, and E2, E1 is what you will get. So dv dt, the first term is, there is no explicit dependence on time here. on these functions, there's no explicit dependence on time. The first term is 0. So the second term will give you the acceleration. So we do this, and this is the acceleration that you will get. It is, if you look at it carefully, it is the centripetal acceleration with the acceleration vector pointing towards the center of motion. Why you get this is something that you should ponder. Remember, we had a square disk that is rotating about its center with an angular velocity, constant angular velocity omega. And what you are saying is, in any rotated configuration at some time t, this is a point x1, x2, and it has acceleration components given by this as the x acceleration and this as the y acceleration. Please think about this problem and see if this makes sense. We have got it through the total derivative. We have got it through a sort of circuitous route, but please try to see if this makes sense to you. Okay, so let me stop here. I will upload another set of lectures for this week, but now we will discuss the previous week's lecture. Let me stop the record.